Okay, so I want to talk about lecture 17. There's an awful lot of content here that I think I should go over in somewhat more detail. It's a very rich lecture, and it does tie together a lot of aspects of the course. So I'm going to be flipping through the lecture here. So if you go, so the first part, he's talking about different applications, audio. We can skip this, and let's go to slide 10. Right, so takeaway here, there's a lot. Okay, so like his usual habit, he's skipping back and forth between continuous and discrete. So let's go back to Laplace transform, which in some ways seems easier to understand. So first takeaway, if you have a system with impulse response h of t, and you feed in an exponential signal of the form e to the st, so I should say a LTI system. This is a linear time invariant system. A LTI system with impulse response h of t, you feed in the exponential signal of the form e to the st. The output is the Laplace transform of the impulse times e to the st. If you remember this thing, that that y is equal to, so this is actually y of t. So he uses big Y for the Laplace transform. So y of t is equal to the Laplace transform of the impulse response. I should say this also, Laplace transform of small h of t times x times e to the st. Okay. Sometimes he writes this as h of s, right? Okay. So you're taking the output function is a constant times the input function. This s is going to be a constant, right? If I have an exponential signal, that s stays constant. It's the time that varies. Okay, so exponential in, exponential out. Okay, so in fact, this is what you call an eigenfunction. When you put in a function and you get out some multiple of the same function, that's called an eigenfunction. And you see those also with matrices. The eigenvalue of or eigenvector of a matrix. You multiply the matrix by the eigenvector and you get a multiple of that same vector. Okay, so these are eigenfunctions. Now the amazing thing is that the same thing you can do with exponentials. Exponentials look like this. You can do with complex exponentials. And complex exponentials give you sinusoids. So the output from a complex exponential input, e to the j omega t, is a complex constant multiple of e to the j omega t. Sinusoid in, sinusoid out. And that's a special property of linear time invariant systems. Now, of course, in the real world, we don't have complex signals. But we can take the real part of a complex signal equation, and that will give you a relation between real signals, right? If you have a complex equation, both the real part and the imaginary part have to hold, right? If I have z equals w, that means the real part of z is the real part of w, and the imaginary part of z is the imaginary part of w. So it's quite amazing. You get an equation that seems more complicated, but each part of that equation actually means something. And the reason why you use complex equations is that both cosines and sines are complex exponential. When you take the real part, they turn into cosines and sines, which are inconvenient. But if you just keep it in complex form, both cosines and sines just look like complex exponentials. Right? So the real part of complex exponentials are cosines and sines. So if we input a linear combination of cosine omega t and sine omega t into a linear time invariant system, we'll get out a different linear combination of cosine omega t and sine omega t. So I did an example here. I just made this up. Suppose your Laplace transform of your impulse response is s squared over 2s plus 1. Okay. So that means, according to what I said above, that if I input e to the st, I'm going to output this Laplace transform times the input. Now, if the input is a complex exponential, I input this complex exponential, and I get out this Laplace transform, but evaluated at j omega, because the exponent here is j omega, right? So this doesn't seem to make a lot of sense. Here you're playing around with complex abstractions, but take the real part of this relation. So the real part of this input is cosine omega t, right? And the output is going to be the real part of this output. Now, if you want to go into the math of why that is, if I have x of t, and that gives me a y of t, and then I take the complex conjugate of x of t, and that gives me the complex conjugate of y of t, then you take the average of x of t plus x star of t. Now, since it's a linear system, the output is going to be the average of y of t plus y star of t. Now, in fact, this is the real part of x. If you take a number and its complex conjugate, add them together and divide by 2, you get the real part. That's a very important relationship that you should know. The real part of any complex number is the number plus its complex conjugate divided by 2. Right? So this is telling me the real part of x is equal to the real part of y. So this derivation actually depends on the fact that if you input the complex conjugate of a signal, you get the complex conjugate out. So it requires that h, in fact, has real coefficients. But in all the cases we've been looking at, that's true. All right? So what I do is I do the complex equation, and then I take the real part at the end. And I would prefer that he would emphasize this enough, is that that's practically how you do the calculations. You do everything with complex exponentials, and then at the very end, you take the real part. All right, so that's what I did here. I take the real part of this complex output, and of course, to make this complex output real, I have to make the denominator real. So I multiply by top and bottom by the same thing. This complex conjugate of the denominator. So I get a real denominator. I have the product of two complex numbers, and I just FOIL that out. And I just need to look at the real part. So I do the real part times the real part, which is the cosine, and the imaginary part times the imaginary part, which the j times j gives me a -1. So this minus becomes a plus. And you can look at that in more detail if you don't get those details. I think I did that right. Right? So what we're saying here is that the input is e to the j omega t. So this is basically a sinusoid of frequency omega. And you get out a sinusoid of frequency omega. So linear time invariant systems don't mix frequencies. If a given frequency is not input, then the output also doesn't have that frequency. So one of the homework problems dealt with that. So they asked you what possible outputs could come from an input. And you can't get a frequency out of nothing. The frequency can only come out if you put that frequency in. The frequency can come in very, very weakly and can go out very strongly, but if you don't put any of the frequency in, you won't get any of that frequency out. All right, so all that we've done with Laplace transforms and continuous signals, and everything hangs together. Now let's do the same thing with discrete signals. All right. So remember the first point here. First point was said, if you have an LTI system with impulse response h of t, you feed in an exponential signal, you'll get out an exponential signal. Same thing with discrete systems. If you have a discrete system with impulse response h of z, now really I should say h of n. Think about it this way. The impulse response should be a signal in time, and this n is your time sample. So you think of h of n as, so if this is time, and I'm measuring time by the index n, then typically the impulse response may look something like this. All right. And you feed in a geometric signal of the form, and let me call this x. We've typically been using x of n. So you feed in the signal of form xn, and the x of n has this geometric shape where z is some number, right? So for instance, if z is 2, it becomes 1/2, 1/4, and so on, exponentially decaying. then the output is the Z transform of this impulse response, which we would typically denote as capital H of Z. So let me say i.e. H of Z times Z to the minus n, right? So compare this with what we had with Laplace transforms. Just take a look at that again, right? With Laplace transforms, the output of the LTI system was the Laplace transform of the impulse response times the input exponential. So we've got the same thing here, only we have geometric signals. Now what's the relation between geometric and exponential? In fact, a geometric signal is a special case of an exponential system. Z to the minus n, if you use your logarithms, by this I mean log base e. Mathematicians use log for log base e. So z to the minus n is just e to the minus log z times n, right? E to the minus log z is the same thing as z to the minus 1. So geometric signals really are disguised exponentials, right? So I have the same condition that I had above with continuous signals, so I'm going to draw the same conclusion. Geometric signals are eigenfunctions of LTI systems. If the input is geometric, the output function is a multiple of the input function. Now, if you remember the next step we had with continuous, we changed z to a complex number. We changed s to a complex number. We can do that with the z also. If z is complex, this still works. In particular, if z has the form e to the j omega t. Okay, right? So I should say, actually I should say e to the j omega. I shouldn't have the t there. E to the j omega. Okay, so the output from a complex exponential input, e to the j omega n, or I could say e to the minus j omega n, it doesn't really matter. Okay, so this is going to be a complex constant multiple times e to the j omega n, right? Again, this n is the time index, so you could think of this, I could write this as x of n, right? Okay, so this is a signal that varies with n, so the output is going to be a constant multiple of this signal. So why do we consider these like this? Because these are discrete sinusoids, right? E to the j omega is cosine omega t plus j sine omega t. Okay, so when you do digital signal processing, waves become discrete sinusoids. So in a continuous signal looks like a wave, but then, looks like a wave. But then when you take samples of this, you end up with something like this. Okay. Now, here's the same conclusion as before. In the real world, we don't have complex signals, but we can take the real part of a complex signal equation. This gives us a relation between real signals. I'm just saying the same thing that I said up there, but now in the discrete world. The real parts of complex exponentials are cosines and sines, so if we input a linear combination of cosine n omega and sine n omega into a discrete LTI system, because we're looking at discrete now, we will get out a different linear combination of cosine n omega and sine n omega. So I do another example with z, and it's basically the same example. So here's the Laplace transform of my impulse response. I'm doing this for a complex z, so it's e to the j omega n. So I replace the z with j omega. And remember, the input j omega n produces this constant times the input. Right? So if you take the real part of this equation, the result's the same as before, except you're replacing t with n. So the same thing is true. Discrete linear time invariant systems don't mix frequencies. If a given frequency is not input, then the output also doesn't have the same frequency. Okay? I'm going to stop here with this video because I'm trying to keep them short, and I'll pick up with the next slides in the next video.